When talking about connectivity in graphs, we talked about K-connectivity, which was a way of describing, really quantifying how robust the connectivity is. And we did it in terms of how much you could remove, like how many vertices you could remove and it would still be connected, right? So a graph was K-connected if removing fewer than K vertices leaves it still connected. Now, you can also ask kind of the opposite version of this question, like what's the least connected among connected graphs? And that leads us naturally to today's topics, which is forests and trees. Let me pull this up. All right, so a forest is simply a graph with no cycles. That's going to be our working definition here. So if the graph has no cycles, then it's a forest. Let me get a bigger marker. And a tree is just a connected forest. So I am guessing that at some point in your academic career, you've encountered trees before. It has exactly one connected component and it has no cycles. That's what we're going to call a tree. Very basic construction. It's tremendously useful in many, many areas of graph theory. We're going to see trees in all kinds of interesting places. In particular, you're going to see a tree inside of other graphs. We'll get there in a sec. Okay, so within a tree, there is a notion of a leaf. And a leaf is a vertex of degree 1. So if the degree is just 1, that means it has just one neighbor. It's kind of hanging onto the tree at the very end. So if, say, this is my tree, something like this. Okay, this little one. This has actually a bunch of leaves. It has 1, 2, 3, 4, 5, 6 leaves in this little graph. Okay, each of these vertices that's hanging off is a leaf. Now, every non-leaf vertex in a graph is a cut vertex. And remember, this is from the definition of K-connectivity. A cut vertex is a vertex whose removal leaves you with more than one connected component. You'll notice that if I were to remove a leaf, the graph stays connected. But if I remove a non-leaf, what I'm going to end up with is multiple connected components. Right? And now let's just prove this lemma. It's not too hard to work out. But we want to do it directly from the definition in terms of the existence or non-existence of cycles. So suppose not. For contradiction, let's just suppose that there's some vertex that has degree greater than or equal to 2, and it's still connected if we remove it. So we have some vertex. Let's give the tree a name. Let's call it T. And the degree of V, strictly greater than 1. And T minus V, that is, if I remove this vertex, it's still connected. Okay, since the degree is at least 2, we can pick 2 vertices in the tree that are adjacent to V. So let's let A and B be adjacent to V. And now the path, there's going to be an AB path. Since T minus V is connected, there's an AB path that doesn't include V. So let's just give it a name. Let's say P is the path. Let's call it an AB path, right? It starts at A, ends at B in T minus V. Again, since it's connected, this path exists. And now P, if we concatenate it with, concatenate, remember that means gluing 2 paths together with the path that goes B to V to A, we have a cycle in T. Now, by definition, T is a tree and therefore has no cycles, and so this is a contradiction. And so we conclude that, in fact, such a vertex cannot really exist, right? We derive this contradiction that we found a cycle in a tree, which should not happen. And so we know that every single vertex that's not a leaf is a cut vertex. And in a way, this means that like trees really are, in some sense, minimally connected. If it's not one of the leaves, every one of the vertices will separate it into multiple pieces. Let's prove some more facts about trees. So if I have a tree, let's call it T, I claim that for every pair of vertices in the tree, there's going to be a unique path between them. Now, the fact that there's a path is not surprising because by definition, we said that a tree was a connected forest, so it had to be a connected graph. So for every pair of vertices, there is a path. But the interesting part here is this uniqueness. Okay, there's just one path. That's path up to isomorphism. So if I reverse it, that's also a path, but we mean unique in that sense. And so the proof here, let me just give the sketch of it. If there were two, so I claim again that the existence of some path is obvious from the connectivity of the graph, but the uniqueness is interesting. So if there were two paths, and again, this is A, B paths, then let's draw what they could look like. So here's A, here's B. So there's some path here, and there's some other path that maybe goes along the same way, but has to be distinct, right? And then maybe it comes back. It can go off again and come back. Then there's going to be some first vertex where they differ. And then there's going to be some first vertex where they meet again after they've separated. And in here is a cycle. So if there were two paths, we can find a cycle, right, in the union of those paths. You can work out kind of explicitly what the parameterization of this cycle would be, but in terms of the two paths, if you like. But the intuition, I think, is pretty clear here, right? So if you had two different paths, since they start together and they end together, but they can't stay together the whole time because they're distinct, right? This is two distinct paths. Then it means that they separate and they come back, and that from there you can create a cycle. All right. If we have any two vertices, we can always find this unique path, and we're going to use these unique paths a lot. All right. Now, here's some other little facts that are kind of good to work through, I think, as exercises. The first is that a tree plus an edge is not a tree. Okay, I'm going to put the proof there in a second, but let me write down the other statement here, and I'll leave you to pause this if you like and think about these two questions, or how to prove these two statements, really. So every tree, I claim, has at least some number of leaves. It has to have at least one edge, with at least one edge. If you just have a single vertex, it definitely doesn't have a cycle. It is connected. I guess we can call that a kind of trivial tree. But if it has at least one edge, then it has at least two leaves. All right, so here are two statements. I claim they're both true. You can pause it if you like and think through how you might prove these. And then I'm going to go ahead and give some answers. First, a tree plus an edge is not a tree. So remember, in pictures here, if I have some kind of tree, if I add an edge, and this is a picture we're going to see again, if I add some edge, let's call that edge, well, let's say it was AB. If that edge was not, again, already in the tree, then we had a unique AB path. We add in the edge AB, and we have a cycle. Okay, so if we're adding AB to the path, remember there's a unique one, but in this case we just need any old one, the unique AB path, we get a cycle. If we have a cycle, then we don't have a tree because trees have no cycles. Easy. Okay. On the other hand, why does every tree have at least two leaves? A couple ways of proving this. You could do this various kinds of induction. Here's one of my favorite ways of proving this. Let's just take a maximal path. Maximal is different from maximum. I just mean that I can't make it any longer. Like I can't add on any more edges and keep it a path. So it's a maximal path in the tree. And let's let u and v be the ends of the path. So this is a uv path. Starts at u, say, ends at v. Then I claim that u and v have to be leaves, and here's why. You see, if there was any edge, if there was an edge, let's call it vw, so if there are any other edges coming out of v besides the last one in the path, right, that's not in the path, I know that it's maximal, so it must be that adding the edge VW wouldn't make a longer path, but in fact would kind of somehow make it not a path, which means it would make it not injective, which means it would make means W had to already be in the path. But that would mean that we have a cycle, right? Because if W is already in the path and T is a tree, then, well, actually, let me give this an even better way. An even simpler way to say this is that because we have a path and W is in the path, right? W itself has to be in the path. That's the only way it would keep us from just extending the path to make it longer. Since W is in the path, I have a subpath from W to V that's in P, right? So there's a kind of this, let's call it P prime, which is a path from W to V inside the path P. And so that means that if I just took that subpath plus this edge, I would have a cycle. So P prime plus VW is a cycle. So that gives me a cycle sitting inside my graph, which was supposed to be a tree, so it shouldn't have any cycles, therefore I have a contradiction. So that's a contradiction. So no other edges are coming out of U and V that aren't already in the path. So U and V are leaves. Okay, so that's one way to think about it. You can also do this by induction. There's a bunch of simple ways of doing this by induction. This is kind of neat because you can think of it as a kind of greedy algorithm where I just start anywhere and I just try to make the path as long as possible without ever coming back to myself. And if I do this, I actually won't get stuck and I'll end up landing at a leaf. And if I started with a tree, and that will actually give me a leaf. So it's sort of a way to kind of just search out until I find a leaf. And in trees, that's what happens, right? If you just start traversing the tree and you don't ever go back, you will eventually hit a leaf. All right, so moving on. So we have a couple leaves. This is kind of this, continuing this botanical metaphor here, right? When we say a rooted tree, talking about roots of trees, should make you think of trees in this botanical sense, but you have to be pretty careful because they're sort of upside down. Usually when we draw a root on a tree, we put it at the top. And this is a vertex, this is a tree where one vertex is designated as the root. So it's given a special name of being the root of the tree. Every other vertex, other than the root, so every other vertex has a unique parent. And the way you find the parent is you just take the path to the root and it's that first vertex you hit. The tree actually can be written now as this pair, right? It has the same vertex set as T. Well, or it has whatever vertex set we started with, but the edges are all of the form V to parent of V. Right, so for V other than the root. Let's see if I can squeeze this in here. So this is for all V in V, T minus the root. Does that make sense? This is a mess. Let me clean this up. Here's how I make paper bigger. So it's v to parent of v for all v in et minus the root. And I guess I could have, I need to make it even bigger, watch. I'm unstoppable. Here we go. Close parentheses. There you go. So that's what it means to be a rooted tree, right? There's this one special vertex, and these are the ones you see a lot in data structures classes. You'll see them like binary search trees. One thing you see kind of immediately, though, from this fact, right? This is really a theorem. It's really a fact that you could derive about rooted trees, some more than it is the definition. But you see that if you were to look at the edge set, there's exactly one edge for every vertex other than the root. And so this hints at a fact that we'll see, which is that the number of edges in a rooted tree, and in fact any tree, is exactly equal to the number of vertices minus 1, right? That minus 1 is minus the root. And so a couple facts about this, you can think of it as it kind of directs the graph. And we haven't been talking about directed graphs so much in this class. But you can kind of think of it this way. And it's used, as I said, in many data structures. If you kind of follow parent to parent, so if I go from a node, a vertex in the graph to its parent, and from that one to its parent, and that one to its parent, I'll keep going until I get to the root. So if you follow the parents, you'll reach the root always. So this is a way to get to, if you have the parents, you can always get to the root. And we use this, we saw this when we implemented depth first search, right? The depth first search or the breadth first search tree really stores a dictionary that has these parent links, and that gives you these paths encoded as a tree in a nice simple way. So we've seen this, right? You should think of DFS and BFS as really canonical, nice examples of rooted trees that show up. Right. So a couple other facts that you should just kind of think about whether you believe these. The first one is that I claim that if you remove an edge from a tree, then it results in a forest with exactly 2 trees. Okay, so removing one edge leaves exactly 2 connected components. If you add an edge between 2 trees, well, then you get a tree. Right, so trees could be constructed in this way by adding one edge between any 2 vertices, one in one tree and one in the other. And you might want to think a little bit about this and convince yourself that it didn't matter what vertex I choose from each tree. If I add any edge, I'll still get a tree. Also, adding an edge to a tree, so if I had a tree and I add just one edge, that creates a unique cycle. We'll see this one in more detail. So there's exactly one cycle. Again, when I say unique here, I mean unique up to isomorphism. Obviously, you can rotate within the cycle within itself and get different cycles, or you could reverse the cycle, but it's the same one. This is like saying it's unique up to isomorphisms, say, of a cycle to itself. Okay, so there are these isomorphisms from a cycle to itself. Right, so if the cycle is C mapping CK into G, it's true that I would get a different cycle by doing C composed H, but it's not an interestingly different cycle. Going along with this, one of the most important kinds of trees you'll encounter is what's called a spanning tree. And it essentially has everything in the name here. It's going to be, well, it has to be a tree. So these are the conditions, right? It's a tree, and it's a spanning subgraph. Remember that a subgraph is spanning if it has the same vertex set, right? So that's saying that VT is equal to VG. Every connected graph is going to have a spanning tree. So within any graph you have, if it's connected, you can find within it a spanning tree. This is not too hard to find. In fact, if you take the graph, there's a simple algorithm you could use to find the spanning tree. Like, for instance, you could do the following. remove an edge. That is, if it's not already a spanning tree. Remove an edge from a cycle. Right, so you start with the graph itself, which is a spanning subgraph of itself. And if it's not already a tree, then it has a cycle and you remove some edge from a cycle. The result is still connected. And so you could repeat. So the proof here really is a kind of induction on the, let me mention this, repeat. It's an induction on the number of edges. If you were to just continue this process, every time, if there's a cycle, you can remove one edge. And this is the key point, right, is that you remove one edge of a cycle, all the vertices on that cycle are still connected. In particular, the pair that whose edge you removed, there's a path that goes around the cycle the other way, and so they're still connected. And so you can just keep doing this until you get down to a spanning tree. That's this idea that there's a unique cycle when you add an edge to a tree is pretty handy. This color didn't print so much. So this is not a tree here. What I did is I took a tree and I looked at this one edge. Now, I've mentioned this, but now we're going to look at it just a little bit more carefully. So if this is the edge AB, there had to already be a path from A to B. And in fact, we proved that there was a unique path from A to B. And therefore, well, clearly we get a cycle, but also it's a unique cycle. Right? So it's for every edge, other than once I have a spanning tree, every edge outside that spanning tree, there's a unique cycle in the tree plus the edge. If you want to check that there really weren't any other cycles, is if there was another cycle, it would have to include this edge, because without this edge, there are no cycles. It was a tree. But on the other hand, if there was another cycle that included this edge, there would have to be another path from A to B, and we already showed that those paths are unique. Right? So this cycles, once you pick a spanning tree T, the cycles you get for all the other edges that are not in the spanning tree are called the fundamental cycles. So you get this collection of fundamental cycles, and it's also not too hard to see how many you get. You're going to end up with one for every edge other than the edges in the tree. So there's going to be one for every edge minus the number of edges in the tree, which is, if we say m is the number of edges here, the number of edges in the spanning tree is n minus 1. So this is m minus n plus 1 different fundamental cycles. And we'll see more about this when we talk about some aspects of algebraic graph theory. All right. And so this idea of adding one cycle and looking at sort of what happens when you add, I'm sorry, not adding one cycle, adding one edge. If you build up a graph starting from like some vertex set with no edges, and you add one edge at a time, you can look at the effect of that edge in terms of connected components and cycles. Really, these are the only two possibilities. Either it connects two components, or it creates a cycle, at least one cycle. Right, so creating new cycles or connecting new components. And this is something we'll also hopefully see again when we talk about algebraic things and topological things. So it's a useful thing to remember, and it's also going to be helpful when doing inductive proofs on graphs. Whenever you do an induction on edges, you can think about what happens when I add exactly one edge. Okay. And so starting from a tree is sometimes handy, adding one edge at a time, and you know you only have one of these two situations. All right, so that's enough for trees for now, but we have at least one more cool topic about graphs that we'll see. And then we're going to start taking our graphs and moving them into other categories, which will be lots of fun. So see you soon.